Manish Biyani to invite me for giving me a chance to great opportunity to present my such work. Thank you. BICON 2015, it was a great conference, nice opportunity to have a chance to collaborate with each other. And so I would like to also thank all of the Indian people, because today I would like to introduce about the relation to the, sorry, I would like to talk about the fuel cell. It's a new technology for energy. Then Professor, Dr. Karthik, he was my postdoc for 1 year and a half. He was graduated at Anna University in India and went to Japan as a postdoc. Then today my introduction of this research is so that he has done, and he was successfully published 3 papers in my laboratories. Then successfully now he is belonging to one of the great institute in Japan, the National Institute for Material Science. He was working now. So today's my outline is first of all, let me have a chance to introduce a brief our JAIST, then going to the fuel cell hydrogen technologies. Then this is the main topic for my research, and with my Dr. Krishna Karthik, developing a proton exchange membrane. This is new type of membrane using the organized structures. And then summary. So first is you may know already our JAIST is not placed in Tokyo or Kyoto. We are placed near Kanazawa city. Kanazawa is meaning of gold. And we are School of Material Science. We have 34 laboratories, physics and chemistry and biology divisions. This is a collaborative research. The energy conversions, semiconductor, simulation, biodevice, artificial cell, liquid silicon, nanoparticles, artificial protein and DNA, solar cell, fuel cell batteries, lithium batteries, functional polymers, medical biomaterials, electronic device, organic electronics, nanocatalysts, surface and interface science, and single molecule research. And also the Professor Oki also demonstrated you. We have a very good facilities. So STEM, so we can see the atomic resolution of the materials by using STEM hardware, and also that we can analyze the chemical composition using the XPS measurement. And also he already showed the 800 very huge NMR, and we have a 3 clean room. Okay, so let's go to the fuel cell. The hydrogen, we are investigating the hydrogen science. So this is from the industrial, the storage material hydrogenation catalyst, and the photocatalyst was producing the hydrogen from the like a seed. And you know the rechargeable battery. This is the hydrogen type, and so we are now developing the hydrogen station in Japan, and also fuel cell. These are based on the hydrogen science. Okay, let me introduce the commercial fuel cell. So these are variable utilization. You can guess easily the vehicle, the fuel cell car, and so we have developing the stationary fuel cell at home, office, hospital, like that. And recently, immediately is the mobile charger using the fuel cell batteries. This technology has improved too much now. Okay, so this is a commercial fuel cell car. Fortunately, we have one of the Japanese companies, Toyota, published a fuel cell car last year, December. So this is still expensive. The left side is we call this car Mirai. This is completely worked by the fuel cell, and this range is 250 kilometers. This is very comparable to the gasoline engine type car, and the maximum speed is around 170 kilometers per hour. And also the Honda is not published, still not published, but that company will be published maybe soon, I hope, another type of fuel cell. And Nissan also developing the fuel cell car. The price is surprisingly $70,000 US. Still expensive, but 5 years ago, this price is 10 times. So that we can reduce 10 times in 5 years. So maybe so 5 years, not 10 times reducing, but maybe so we hope that is much cheaper to improve the material and the fabrication technology of the fuel cell. So now the government supported 20,000 US. So that we can buy this car 50,000 US. But unfortunately the reservation is very much now, so we need to wait at least 1.5 years when we order. So so the time for the hydrogen charge is very short, so 3 minutes. So that this is the hydrogen type fuel cell car, maybe so very similar, very applicable, very useful, with comparable to the gasoline engine car. Okay, here is the mobile charger. Recently developed too much because this is very applicable to the industry. So now, 5 years ago, the fuel cell mobile battery is based on the methanol type fuel cell. But now, you see the fuel is butanol gas. The charging time is only 3 seconds, not 3 minutes. Just you push the relatively pressure gas of butanol, so you can charge immediately. Then 3 seconds charge you can use as battery. For example, number of charge for iPhone example 10 times. 3 seconds charging, so 10 times chargeable. So this is amazing. And also you can take this carriage in the aircraft cabin. So no problem to go overseas with this. Okay, stationary. So this is already started to commercialize and at home to hospital, office, hospital, anywhere. The fuel is fortunately we use normally the methane or propan as a fuel, not only hydrogen. So we can use the methane propan. So this is very convenient for the home. So we can use the methane propan as a fuel to this stationary fuel cell. So the conversion efficiency is more than 90. The Japanese government is planning to introduce to the 10% reduction in all Japan residents, to introduce this type of stationary fuel cell until 2030. Okay, so this is general information. This was general information. So let me back to the fuel cell. This is a polymer electrolyte fuel cell. So you can see this fuel cell like schematic view. So the fuel cell composes the electrolyte of the catalyst layer. We call the hydrogen gas side as anode, then the cathode side is oxygen side is cathode. So the hydrogen was reacted on the surface of that black catalyst layer, then produce the proton. But today's my talk is proton is very important. The proton can be transported to this blue region, the electrolyte. This is membrane, so completely separated oxygen and hydrogen. And then proton transport to the cathode side, then meet the oxygen on the platinum surface. That is electrocatalyst. Then produce the water. So now proton transport is one of the key technologies. So proton transport is used in the electrolyte, this blue region, and you see that this is magnified three-phase boundary. That is reaction site of the fuel cell. Ah, thank you. Okay, three-phase boundary here. You can see the white one is the platinum electrolyte chemical catalyst, and the blue one is also the polymer proton exchange membrane. Nafion normally so we use. I will introduce later. This is membrane electrolyte, and here is ionomer. This is also Nafion, but this is quite different properties. But anyway, so the proton transport is one of the key technologies. Okay, let me introduce Nafion. This is a very commercial, normal fuel cell, very commercialized already. The proton exchange membrane for fuel cell, the Nafion, the chemical structure is shown here. The main backbone chain is the hydrophobic. And at the side chain, this is hydrophilic. So we can have phase segregations between hydrophobic and hydrophilic. At the side chain here, you can see the red one. This is sulfuric acid group at proton source. So this membrane can absorb the water. Then this is the schematic views. The white is the water nanochannel. This is relatively 1 or several nanometer width. Yes, yellow one is the hydrophobic part. This is the micro segregations. This is a schematic view using the analyzed by the small angle X-ray diffraction. Small X-ray scattering. This is the actual views using the cryo-chem. So this is a very recently published. So the actual view and the schematic view is very similar now. So Nafion is very useful. But unfortunately, we found that this Nafion's proton transport, this is proton conductivities. So this is decreasing at the interface. I mentioned about these regions, not these regions. These here at the reaction site, this ionomer, the proton conductivity decrease. You see that this is relative humidity. This means related to the water uptake. The water uptake, then this is the low proton conductivities. So you see the black one, this is very high, into the -2 was Gms. This is a proton exchange membrane, but as ionomer, the material is same, but this red one, blue one is ionomer, quite decrease at the surface we found. So that maybe so that we have a chance to improve the fuel cell if we can develop another type of ionomer. So the issue is, one of the issues is interfacial proton transport type. So we are investigating now with Dr. Kartik. So our research interest, okay, so our research interest is controlled proton using organized structure. The organized structure is keyword in my talk. So most of the researchers, many researchers already investigate the conductivity for fuel cell, but cannot control it. So So now we are focusing the unexplored field for the proton transfer, the anisotropy dimensionality, using the protein in higher order structure hierarchy, storage, rectification, switching. So fortunately, we have successfully published some papers using this concept to enhance the proton transport. Okay, here is the video movie. So our goal using the organized, the structures. So we designed the polymers. The polymer can assemble automatically, self-assemble. So this needs, of course, the driving force. We can design like this, fabricate like this. Then using these technologies to apply the more oriented device. So using the bottom-up and the top-down technologies to fabricate, like using the inkjet printing, then fabricate the new type of device. So this is an example of the fuel cell. This is a new type, totally new type fuel cell. But hydrogen can react it to meet, proton can meet the red oxygen to produce the water. Very high performance. Now we are trying to this project to collaborate with India One Institute. Okay, here is a recent publication summaries. Proton transport at interface. In the case of Nafion, so unfortunately the conductivity decrease, so that is not suitable material as ionomer. But we found the amide oligomers and the polypeptide. This is artificial polypeptide. And so today I would like to introduce the polyimide. This is highly increased proton conductivities if we are focusing on the interface. Okay, so let's move to the how to create the proton conductors. So I would like to ask you, this is sulfonic acid. So in this acid, so normally the answer is yes, but if water exists as an acceptor, so this means sulfonic acid itself does not work as acid. But if the water exists, this proton can move to water. So that is meaning of the acid. Okay. So the sulfonic acid, the acid proton can move to water side as an oxonium ion. This is a proton transport. So if the more water comes with hydrogen bonding, the proton can easily to move another water. By using this concept, going to the proton goes through the hydrogen bonding system with water molecules and come back easily to the sulfonic acid side. So this is a proton transport. Now, so you have a concept this, so that you can make proton conductors by using this concept. So here is the schematic view. Sulfonic acid and waters. The sulfonic acid is a donor, and the water is acceptor. This proton can be received by the water. This proton, white one is a proton. Then, if you can arrange this, maybe you can have a highly proton conductive material. So, if we can make a nanochannel, water nanochannel like this, so donor layer, acceptor layer, donor layer like this, maybe the high proton material, but you need to bond each other. So we need to introduce polymer. So this is needed to bond. So you need to bond here, green one. Then drawing again. So this is the ideal structure for high proton conductive material. So using this donor and acceptor concept. So this is the side chain sulfonic acid group. This is the water layer. like this. So how to make this? So this is the finally obtained today's my talk is the sulfonic aromatic hydrocarbon based polymer. This has a water nanochannels and bilayer of the polyimide backbone. But we need a driving force to make organelle structures. So we need some idea, but today I will introduce to make organelle structures using lyotropic liquid crystal properties. This is the driving force for the organelle structures. So you see this is figure, this is the concentration temperatures. The molecules, the concentration is very low, it is separated, but if the concentration increases, the many kinds of the organized structures obtained. So this is the phase segregations we use by different intermolecular interactions. So by using this concept, you can see that everywhere in your life, the micelle, bilayer, membrane, like a soap, and polymer blend, block polymer, everywhere. Okay, by using this concept, let me introduce the polyimide. What is polyimide? Polyimide like this. The polyimide, the characteristic is rigid main chain, very rigid, and high chemical stabilities applicable to the industry, and also the 5-5 interaction. So this is like aromatic, many aromatic. So that this is like a Prada structure, easy to assemble like this. By using, introducing the sulfonic acid group as a side chain, yes, this is a high proton conduction. This is already known, not our work. But the structure is unknown, totally unknown. So we found that the structures, the solubilities, are also improved so that we can make any shape and the liquid crystal property of that. To make a simple, very easy technique. So using the plasma cleaning to make a hydrophilic surface on the substrate. Substrate is shown here. Like this. This is hydrophilic, this is water. And the spin coating so that we can fabricate very good thin film. The thickness is around 500 nanometers. Okay, to confirm the organelle structures, so we can use the RH in-situ. This is relative humidity in-situ, grading incident, small angle X-ray scattering. This is the example of the polyimide case. This is not ours. Without sulfonic acid group, yes. So the X-ray comes here. This is simple. The scattering to the two-dimensional imaging. So we can see this is the out of plane direction. This is in plane direction. So Professor Aldo suggested from this data so that this polyimide might be organized structures, like using the liquid crystalline properties. This is the actual our data with sulfonic acid group. So you can see the two-dimensional and the dry condition, humidified condition. This is in plane. In plane means here, cross-sectional. Then out of plane is this directions. So you see the black and red, 0% humidity dry to the increased humidity, red one. But the in plane diffraction does not change. But out of plane cases, so this is different. From the dry to the red one, so you see that this peak are moving to the lower value. So this means totally anisotropic structures. So by analyzing this, we can see the lyotropic lamellar structure based upon the liquid crystal properties. So here is again shown the organized structures. So you see this is in plane 1.6 nanometer. This is correspond to the unchanged peak here. This is polyimide, so please don't see this. And this peak is correspond to this direction. So this meaning increases the humidity. That is, the water comes inside of this polymer. So that the water can introduce here, then expand this direction. So this meaning of the changing value is corresponding to this expansion, so that we can see the 1.3 nanometer very thin nanochannel for proton transport. Okay, so here is the proton conductivity investigations. You see the humidities. This is the proton conductivity. The blue one is the Nafion. This is conventional Nafion fuel cell membrane. So fortunately, this is the red one is a very high conductivities compared to this Nafion. So this is the first to demonstrate how organized structure is contributable to proton transport properties. As a future work, so now we have a material. Then we would like to apply this material to the ionomer. I hope that this is a very suitable ionomer. So we can enhance the fuel cell performance using this organized structure. And also the more important thing, now we have an organized structure, not amorphous structure, so that we can have a chance to control the proton. So using anisotropy dimensionality, switching rectifications like this, so that we are trying hard now to investigate, to develop this new type of proton transport material. So let me summarize. For developing the hydrogen science, the one is to improve the fuel cell performance. New concept using the organized structures has been established. So this is already established. And successfully synthesized organized structure to polyimide using the Lyotropic liquid crystal property. This is the first report to how the proton transport very high using the organized structures. And this is the value is very high proton conductivity. This is comparable to the liquid 1 molar hydrogen chloride, very high acidic condition, but that is simple, not liquid. Okay, I would like to acknowledge Dr. Kartik Krishna and my student, Yuki, attended this nice conference. So he has a poster. So please, if you are interested, please go to his poster. I'd like to thank some research budget. Here is my research group. Half are international. We welcome you if you want. So unfortunately, I don't have any experience to receive Indian students. We have already 2 Bangladesh near your countries. Very nice students. So please, thank you very much.
Thank you, Professor Nagao, for your wonderful work on fuel cells and how it is important to, by organizing the thin layer, we can improve the conductivity and can make more efficient fuel cells. So now we are open for some theories and to see how you understand the lecture, especially from the young minds. Anyone? Oh, yeah, please go ahead.
So my question is, why do we use only sulfonic acid groups for proton conducting devices?
Sorry, what kinds of acid?
So why do we use only sulfonic acid groups for proton conducting devices?
Using the sulfonic acid group, then what do you want?
Why do we use?
Increase the humidity, red one, but the in-plane diffraction does not change. But out of plane cases, so this is different. From the dry to the red one, so you see that this peak are moving to the lower value. So this means totally anisotropic structures. So by analyzing this, we can see the lyotropic lamellar structure based upon the liquid crystal properties. So here is again shown the organized structures. So you see this is in plane 1.6 nanometer. This is correspond to the unchanged peak here. This is polyimide, so please don't see this. And this peak is correspond to this direction. So this meaning increases the humidity. That is, the water comes inside of this polyimide. So that the water can introduce here, then expand this direction. So this meaning of the changing value is corresponding to this expansion, so that we can see the 1.3 nanometer very thin nanochannel for proton transport. Okay, so here is the proton conductivity investigations. You see the humidities. This is the proton conductivities. The blue one is the Nafion. This is conventional Nafion fuel cell membrane. So fortunately, this is red one is a very high conductivities compared to this Nafion. So this is the first to demonstrate how organized structure is contributable to proton transport properties. As a future work, so now we have a material. Then we would like to apply this material to the ionomer. I thought that this is a very suitable ionomer. So we can enhance the fuel cell performance using this organized structure. And also the more important thing, now we have an organized structure, not amorphous structure, so that we can have a chance to control the proton. So using anisotropy dimensionality, switching rectifications like this, so that we are trying hard now to investigate, to develop this new type of proton transport material. So let me summarize. For developing the hydrogen science, the one is to improve the fuel cell performance. New concept using the organized structures has been established. So this is already established. And successfully synthesized organized structure to polyimide using the lyotropic liquid crystal property. This is the first report to how the proton transport very high using the organized structures. And this is the value is very high proton conductivity. This is comparable to the liquid 1 molar hydrogen chloride, very high acidic condition, but that is simple, not liquid. Okay, I would like to acknowledge Dr. Kartik Krishna and my student, Yuki, attended this nice conference. So he has a poster. So please, if you are interested, please go to his poster. I'd like to thank some research budget. Here is my research group. Half are international. We welcome you if you want. So unfortunately, I don't have any experience to receive Indian students. We have already 2 Bangladesh near your countries. Very nice students. So please, thank you very much.